Welcome to the Water Resources Podcast. I'm Bridget Scanlon, and in this podcast, we discuss water challenges with leading experts. And I'm really pleased to have Richard Taylor with us today, who is a professor in the Department of Geography at the University College of London. Richard, you have devoted most of your research career to understanding water issues in developing countries. And today I think we will focus on Sub-Saharan Africa. So thank you for joining me today.
Thank you for inviting me. I'm delighted to be here.
Right. And so, Richard, we've been hearing a lot in the last couple of years about a drought in the Horn of Africa and the lack of the rainy seasons and the concerns about potential famine. And then linkages of that with El Nino Southern Oscillation climate indicators like La Nina conditions persistent over the past few years and finally breaking this spring. Much of your work has also looked at linkages between climate and groundwater resources. So maybe you could describe a little bit about your work in that realm and then what you have learned about El Nino and its impacts on water resources in your studies.
Yeah, the research that we've been undertaking, particularly in areas such as Eastern and Southern Africa, it's been looking at observation. It's been focused on observations and trying to develop an observational database. One of the clear links we've been making through that has emerged through the analysis of that observational database is these strong associations between heavy, extreme rainfall and positive deflections in groundwater levels. So groundwater level rises that are indicative of recharge events and these seem to be biased to the heavier rainfalls. And the connection between the heavy rainfall and these large-scale climate anomalies or controls on climate variability, such as ENSO, the El Nino Southern Oscillation, but also in this context, the Indian Ocean Dipole that operates in the same area. And you pointed out earlier that the period of drought, which is actually just broken in the Horn of Africa, and they've recently, since March, had some heavy rainfalls. This is actually somewhat typical in what we've encountered in drylands, in which you have often kind of multiple years of perhaps low rainfall that is interrupted, if you will, by years of either much less rainfall or much increased rainfall. And what we've seen in Eastern and Southern Africa is a sort of interesting connection with ENSO and the Indian Ocean Dipole. And as you indicated earlier, the rains in East Africa heavier rains are often associated with El Nino years. And that actually switches in Southern Africa. So in Southern Africa, for instance, during El Nino years, you will experience drought. And so in La Nina years, East Africa will also experience drought, but then Southern Africa will experience heavier rainfalls. And one of the interesting things that we've done by interrogating the time series of groundwater levels is that control on rainfall, and particularly heavy, intense rainfalls, be it seasonal, sometimes monthly, or even daily, a series of events over a few days. These are represented in the piezometric time series. A really good example, maybe I'll focus on that just for a moment. We have a situation in central Tanzania. The capital city of Tanzania is Dodoma. It depends entirely upon a well field for its water supply. And in the mid-1990s, after quite a few years of low rainfall, below average rainfall, there followed the most intense El Nino event of the 20th century in 97-98. And over a 5-month period in central Tanzania associated with very heavy rains, exceptionally heavy rains, over 25% of all the recharge that occurred over a 60-year period happened in 5 months. So it's, and it basically topped up the well field. There was an 8-meter rise in the groundwater levels in the well field. The groundwater levels in the well field returned back to that pre-97, 98 El Nino year 20 years later. So I guess what I'm trying to highlight to you is the absolute importance of sometimes those extreme events in the replenishment of these aquifers. What it means, though, is in drylands that it, from a kind of governance perspective and from a kind of understanding the renewability, something that you and I have spoken about in the past is a bit of an allergy to reporting recharge rates as some sort of annual rate. And actually the work that we published in Nature in 2019, we were encouraging people to start thinking about recharge on decadal scales at least, and reporting them that way so that people don't think, engineers or others trying to understand the renewability of groundwater resources, thinking if they are basing their understanding of renewability on an annual rate, say, I don't know, 50 millimeters per year. If you think you're going to get 50 millimeters per year, you're going to be sadly mistaken, because what it could happen is you might have 7 or 8 years of almost zero, and then you might have 500 millimeters in one event in a decade. And so it's trying to understand the episodic nature of replenishment in drylands.
Right. I think that's fascinating. And these long-term records really help with that. And I can recall taking a taxi in Austin in the late 90s and talking to the taxi driver. And it turns out he was from Kenya. And he was talking about the flooding that occurred during El Nino in Kenya in 97, 98, you know. So I think it helps to talk to your taxi driver when you're in the mood. But you know, I've just been talking to some folks from Australia, and so during La Nina conditions, then we have drought in East Africa, wet conditions in Southern Africa, but also flooding, a lot of flooding in Eastern Australia during those years that we had La Nina. So understanding these connections between El Nino Southern Oscillation and precipitation and water resources helps us to manage these resources then and try to understand when we might get out of a drought and when we should take advantage of flooding conditions and try to capture some of that water. So another aspect of your work is looking at projections for the future. And so we hear a lot about increasing climate extremes with climate change. So more longer term droughts, more intense droughts with higher temperatures, and then more infrequent but more intense flooding. And so your work then has looked at how that might impact groundwater resources. Can you describe that a little bit?
Yeah, I can, because one of the big concerns, really, if we're, as we know, a universally observed impact of warming is this transition to fewer but heavier rainfalls, and it's a transition that's actually most intense in the tropics and by extension subtropical regions. And so, under those conditions, they are essentially perhaps disfavoring surface water resources and also affecting soil moisture. And so what we are seeing is a situation, particularly as many areas in tropical Africa seek to expand areas of the areas of their arable land that are irrigated, and trying, of course, because this shift between fewer but heavier rainfall events has a very big impact on soil moisture. And given that almost all the agriculture that takes place at the moment in tropical Africa is rain-fed, this has a very serious, poses a very serious threat to food security. And so one of the ideas, of course, is to become more resilient to fewer but heavier rainfalls, is to move towards an expansion in the irrigated areas. So this means, obviously, greater use of water. But if your surface water, particularly, let's say, your river flow, is more of it is evaporating, and less of it is around, particularly during the drying season. This is now shifting attention to perennial water sources, and of course, particularly perennial water sources in drylands, which are in almost all cases going to be groundwater sources, although there are some exceptions to that. And so it's recognizing how important these heavy rainfalls are to that replenishment. And what I can tell you is, in light of also with kind of not only with the aims for expansion of irrigated agriculture, but also increasing the amount of the availability of water on a domestic level, but also for industrial growth. This kind of increased freshwater demand is posing serious questions about how it's going to be met. And so one of the ideas that people are beginning to look at, particularly in light of our earlier conversation about its connection to what we might refer to as large-scale climate controls on climate variability, is if we now can anticipate ENSO is going to, or an El Nino year is going to produce heavy rains in East Africa, is there some way that we might be able to give nature a little bit of a helping hand and perhaps begin to think of some clever interventions to kind of increase that freshwater capture that we can take from those periods of heavy rains for use later in times of need? And then recognizing, of course, that when you have an El Nino year, that's going to mean drought in Southern Africa. So areas such as Mozambique, South Africa, Botswana, Zimbabwe. And they can therefore begin to think about kind of seasonal responses. Of course, we all were familiar with Cape Town Day Zero and how the city had to radically engage in some demand-led interventions to try to avoid running out of water. But beginning to think of this as, oh, okay, we got to be a bit more conservative in our water use this year because it's a La Nina year, or it's an El Nino year in Southern Africa when we're not going to get much rainfall. And I think that's why identifying these large-scale connections is very helpful. Of course, it's not always the same. There's some obviously uncertainty and unpredictability. Some parts of East Africa may not experience especially heavy rains, and some parts of during an El Nino year, and some parts of Southern Africa, vice versa, on a La Nina year may not experience. But generally speaking, we do see these trends, and they are reflected in river discharge and in the groundwater levels.
Yeah, I like it. I like your point that you make that with these increasing extremes, so we're either in a drought, long-term drought, or a flood, intense flood, that we're going to have to do more to manage the water resources and to even out that water supply availability. And I think, some people may find some of your findings a bit counterintuitive, because you think with these flooding extremes then that most of that water would run off. But in these dry lands, then it allows water to pool and to exceed the evapotranspirative demand of the high temperatures, and so get down below the root zone and recharge the aquifers. That's why we see these episodic recharges with these heavy events. They can exceed, because if we just had drizzle all the time, then the plants would just use it up and we might not get hardly any recharge. But with these very heavy extremes then, and they're projected to increase with climate change, then we might see more groundwater resources, and that would be a positive, for people who are reliant on
some people refer to that sometimes as effective precipitation, and this idea that the surpluses, some people refer to it as blue water, those sort of blue water surpluses are quite critical to the water budgets and the water balances. I think it has important implications, because if we sit with the paradigm that all replenishment is diffuse, we can then run into some problems. Okay, and I'll give you an example. So in the well field in central Tanzania, there's really no relationship between local rainfall and the groundwater level fluctuations that we observe in the groundwater system. And and that's a bit puzzling, but actually it has very strong connections and statistically significant ones with the rainfall in the uplands 30 to 50 kilometers away. And the explanation really is that it's the net surplus that's happening in the uplands. Evapotranspiration rates are a little lower. Of course, moving up in elevation, the precipitation is a bit higher. You have a net surplus coming from those uplands, draining into the lowlands, and then leaking, okay, from those river channels. And of course, overbank flooding, allowing and identifying different pathways of then infiltrating and replenishing the well field. And it's recognizing that form of recharge, which we call focused recharge, where it's not happening throughout the landscape, but it's restricted to a particular part of the landscape, a river channel or the adjacent to the river channel. It's recognizing the importance of that. And I say that because the curious thing in Dodoma is they have a wellhead and well field protection area. And very curiously, the wellhead and well field protection area is right around the well field, and not in the upland catchment where the surpluses are being generated. So actually what the outcome of this is to explain and help the ministry understand that you need to think of catchment scale management, obviously, of your water resources, and that your well field depends upon those surpluses and those water balances that are occurring remote from the well field, quite some distance away, where you're generating that river discharge. And that's a really important bit around governance of the system itself, so people understand how important the water surpluses, the runoff being generated in areas upstream. In fact, that kind of dynamic of a kind of relatively humid or subhuman uplands and a semi-arid to arid lowlands is a very common dynamic in many parts of tropical Africa.
Right. And I think that's great. I mean, I live in Austin, and sometimes you're driving along the highway and you see now crossing the Edwards Aquifer recharge zone, you know, and they try to protect the recharge zone, and that's oftentimes not co-located with where the aquifer is. And so these sorts of things are very important. So it seems like your research then highlights the spatial and temporal disconnect between water moving into the system and, you know, your supplies. So maybe, Richard, you can describe a little bit. I know since your PhD work, you've been doing field studies, and maybe you can describe something about the tools that you use. How do you monitor the groundwater levels, and what other tools do you use to understand this groundwater resources, the dynamics?
Yeah, thanks, Bridget. One of the things that we kind of recognize is that I'll say high frequency, so very regular monitoring of groundwater levels was not a particularly common practice in many parts of the world in the past. And it's only really since around the 1990s and since where we've begun to see higher frequency time series and continuous time series of groundwater level observations. Of course, there are some places on the planet where these are, you know, weekly or even fortnightly time series. But I guess what I wanted to say is there's the piezometric database. So time series records of groundwater levels have really, we're beginning to generate those. And myself, working with ministries in Uganda and Tanzania and other places in tropical Africa, we installed monitoring wells back in the early 90s as an example, and they now have 30 years of records. So you can now actually look at kind of climate groundwater associations. You couldn't do that, you know, when you only have a few years of data. But one of the things that these have begun to reveal some interesting things. First of all, what we've already been talking about, this kind of bias in the tropics of groundwater recharge to heavy rain events, whether we're talking about humid areas or in drylands, semi-arid to arid locations. There's another aspect of this that I think is important to raise, Bridget, and it gets back to your comment about the kind of perhaps curiosity people might have of, shouldn't heavier rainfalls generate more runoff, not more recharge? And I think one aspect of that, and I will say this, is what the piezometric records are beginning to show is responses, lagged responses to rainfall events, but the lag is not very long. It's in the order of sometimes hours to shallow ones, to say days to a couple of weeks. And what that means is the water is moving through the vadose zone, the unsaturated zone, down to the water table. And I'm talking about water levels that may range from, say, 5 meters down to, say, even 30 meters. What we're seeing is the, if you want to call it lag time, response time, or the travel time through the vadose zone is much shorter than we would expect using the Richards equation as an example, or assuming that the infiltrating water is sampling all of the pore space. And I think particularly in the weathered crystalline rock aquifer systems that occupy more than half of tropical Africa, you have quite heterogeneous soil systems. And so the notion that there is some sort of infiltration capacity that is representative of the capacity of those soils to transmit water, it doesn't really hold. Now, we, of course, in some environments, very well unconsolidated, very well sorted, unconsolidated sands, alluvial systems, dunes, yes, perhaps they do sample much of that pore space, but I think what we're finding is more often than not, the water is moving through preferential pathways, what Keith Bevan has for a long time been calling soil macropores. And he long has argued that the role of soil macropores in our understanding of the hydrology of the subsurface is very much underplayed and not fully, not sufficiently appreciated. So I guess what my rejoinder slightly to the hydrology community is, the piezometric records are telling us that actually the replenishment pathways are probably dominated by preferential pathways through the unsaturated zone, rather than sampling the whole pore space. This has important implications for the modeling community, which may be employing a particular infiltration capacity and having this concept, heavier rains must mean that more water is running off, not infiltrating. But that's probably operating on the assumption of there's some consistent infiltration capacity that defines the soil, when actually we're finding much faster replenishment rates. And this actually leads on to another point. So in addition to the piezometric records, one of the things that we've been beginning to do for some time now is to time series of water quality monitoring. And what we're seeing is shallow groundwater contaminated by heavy rainfall events. Now, and I should point out, a lot of this contamination is fecal. So we're seeing the flushing of fecal matter, whether it's animal or human, moving through a unsaturated soil zone in the space of hours to a few days, so that they are still viable when they're pumped from a well with a water table depth of, say, 8 or 10 or 15 meters. And what that's also telling us really is that it's a kind of confirmation of the rapidity or the speed with which these heavy rains are actually finding their way through these soil structures and getting down to our aquifers. So actually groundwater, I think in many cases, particularly in urban environments where the pollutant sources are greater, are quite vulnerable to contamination. And we need to kind of appreciate that the groundwater is maybe more vulnerable than we previously thought to contamination. Maybe I'll just say the last bit, which is a curious one for the tropics, in terms of the evidence base for heavy rains connected to bias to groundwater replenishment is, and this goes back to some early days of myself and a few other people who had done this work, we noticed that groundwater, sampled groundwater in the tropics, in many places, particularly in tropical Africa, had a different chemistry to the weighted mean average isotopic composition of rainfall. We thought to ourselves, how is that possible? So the explanation becomes a bit clear when you recognize that the isotopic composition of rainfall in the tropics is dominated by an an effect called the amount effect. Heavier rainfalls are depleted in heavier isotopes. So when you sample rainfall, you'll notice that those really heavy rainfall events have fewer atoms of oxygen 18 or deuterium than lighter rainfalls. And actually, when you sample the groundwater, it is depleted in heavy isotopes and compared to the weighted mean average composition of rainfall. And the most logical explanation is that there's a bias in the replenishment of the groundwater to the isotopically depleted, heavier rainfalls. And we've not only seen this in tropical Africa, but we've seen this across the tropics. And so the evidence base is now really quite compelling. It not only involves piezometric responses, so monitoring well records that are showing disproportionate responses to heavy rains. And then secondly, we are seeing that wells and springs are contaminated, often quite rapidly, in response to heavy rain events. And then thirdly, we are also seeing that the basic chemistry of the groundwater is much more strongly connected to heavier rainfalls than all rainfalls. And so it's a pretty, in its entirety, is a pretty compelling evidence base. And maybe I'll stop there. We can maybe move on to some of the gray stuff in a moment.
Right, right. So I really like the way you bring in multiple lines of evidence to try to constrain your conceptual understanding of how the water system is working. So the simple groundwater level monitoring, and I'm sure you have the professors that are in these universities now have students going out and monitoring water levels. I did that when I started my master's work way back in Ireland. You know, I went around in my bicycle and I had my water level recorder in the basket in front and would stop off at all these houses and monitor water levels. But it gives a wealth of information. Then we installed recorders to monitor water levels automatically in some regions and have those data to look at. And so it's very impressive now that you have about 30 years of data or more in some regions, and you cannot replace those data, and they're extremely valuable in trying to understand how the system responds to climate conditions and rainfall and droughts and stuff like that. So the other aspect of your work that I think is very impressive is that you're not just looking at water quantity, you're also looking at water quality, which is very important. And sometimes we think, you know, if we have a heavy rainfall event, maybe we would dilute the contaminants and we would, the dilution effect would work and we would see lower contamination. But actually what you're seeing then is that these heavy rains are flushing contaminants into the aquifers after these heavy rains. So, and then this idea that, you know, the soils are cracked and these macropores allow water to move rapidly through the soils. So a thick soil zone is not necessarily going to protect the groundwater from contamination, but also would favor recharge. So from a water quantity perspective, it's good. But we also have to be aware of water quality implications. So, you know, people were so gung-ho on macropore flow and preferential flow when we did some studies in the high plains in the US, and we could see that a chloride that had built up in the soil profile from thousands of years of evaporation, and then when they converted it to cropland, then it moved that down. So it moved it down like a piston. And that was so unusual because people were so, you know, they had been thinking about macropore flow all the time. It was difficult for us to convey that concept that really it's moving uniformly in these soils. But so it varies. So climate and its impact on recharge and this preferential flow, and then the implications of that for water quality are extremely important. So a lot of these studies, and as hydrologists, you know, we look at borehole data, we like to monitor wells and small scale. So then along comes satellite data like GRACE, And it's sort of difficult for us to wrap our heads around that and to try to get the value out of it. But maybe you can describe some of your work with others like Shams and others on the GRACE data.
Yeah, so that was one kind of curious thing that we were looking at was what is the situation between kind of local scale observations from piezometry to much larger scale, so GRACE operating at about 100,000 square kilometers. And yes, and this work really took off a bit working with a PhD student and then a postdoctoral fellow, Dr. Mohammed Shamsadua, who is also here at UCL in the Institute for Risk and Disaster Reduction. And working with Shams, we were interrogating and we looked at the global data set to try and better understand the kind of episodic nature. Can we see evidence of this episodic nature operating not at the scale of a well, but at the scale of a region? And what was quite curious is that even in a much, we might call it blunter instrument operating at such an integrated level at that scale, what we found was that the evidence for its bias to heavy annual or monthly rainfalls in humid regions was more difficult. The evidence was perhaps a little too fuzzy, but we still, in drylands, we do see and resolve that the groundwater storage increases associated with heavy rainfall are evident in drylands and in semi-arid and arid environments. And I thought that was a really important way to kind of connect the smaller scale responses to that larger scale. I think an important thing we need to raise, because many people were saying, hang on here a minute, I thought people had associated GRACE with identifying depletion. And I think one of the things that I would say is that, of course, when we think about the sustainability of groundwater resources, these are big kind of societal questions. And groundwater itself is renewable in many places, some places less so, but is renewable. But if our deliberate efforts to pump much more than is renewable happen, then of course we're going to encounter groundwater depletion. And I think more broadly, one of the big concerns is that we find in dryland environments, whether you're looking at GRACE or even at the piezometric evidence, there is unfortunately places like Iran, North China Plain, the Southwest United States, and the California Central Valley. You know, we do know, and it's been very well documented now, the depletion that's being taken place, and of course this has led to important adaptations, I'll call them, to the new legislation that's operating in California. But just a word of caution that it doesn't mean that groundwater is depleting in all semi-arid or dryland environments. So there are other locations on the planet where where much less well developed in terms of the amount of water being pumped out, where in drylands water levels are not undergoing depletion. And I think one of the big efforts we need to think about now is not only to address depletion in the areas where it is observed and pronounced, but also to provide sobering lessons to other dryland areas of the planet that, yes, you do have perhaps a groundwater option, but do not necessarily follow the same pathways that we have followed. And I think one thing that you had mentioned to me earlier, we were both really impressed with the work that's been done in the Sahel, where our colleagues there in places like Niger have uncovered actually groundwater accumulation taking place, and then diagnosing this to changes in land cover. So we recognize that that groundwater systems are not simply a function of pumping and precipitation. They're also influenced, of course, by changes in land cover. And yeah, I think the Sahelian paradox as it's called there, where under conditions of reduced precipitation, they had increased river flow and rising groundwater levels, is a interesting and an important recognition that the water balances are not just dictated by precipitation, but land cover responses and the use of and evapotransport demand are important in doing that. And I think we're both aware that that Sahelian paradox is explained by the fact that they transform very large areas that were cleared of their perennial grassland cover and replaced with shallow root crops, which ultimately, particularly at periods of the year, had a much lower evapotranspirative demand, and therefore there was a net surplus that was not delivered by extreme rainfall, but by reduced evapotranspiration.
I think you make a great point there, Richard. You know, we started off talking about climate impacts on groundwater resources and the linkage to El Nino and other climate teleconnections. But then human impact, which we've seen in different regions globally with the hotspots of depletion that you mentioned in the Central Valley and other regions. But humans can also impact groundwater resources through land use change. And that's Guillaume Favreau and his work from IRD in Niger really shows that. And also we've seen that in the Southwest US, increased recharge when we converted from native vegetation to croplands, because part of the year there's no crop growing. So there's no evapotranspiration. They've seen it in Australia, many regions it occurred long ago, but it's much more recent in West Africa. So the GRACE data, even though hydrologists were not familiar with using large-scale data, I think it shows the dynamics, and a colleague here, Ashraf Ratib, has linked the dynamics of the GRACE water storage changes to ENSO, El Nino, Southern Oscillation, North Atlantic Oscillation, and Indian Ocean Dipole, and looking at those connections then to understand the linkages and the dynamics of the water storage. So I think that has been very helpful. Another aspect, and I know you're heavily involved with this, is the United Nations had an emphasis on groundwater recently, and they talked about making the invisible visible. So the UN oftentimes relies heavily on global models, and you mentioned those recently, and the fact that they were not capturing some of the processes that you see from your field studies. But do you see that the global modelers are starting to incorporate some of these ideas into their modeling, or do you think there's potential in the future that they will incorporate those and then maybe more reliably represent what is going on?
I think so, and I think it's the hydrology of focused recharge in itself. How do you incorporate, for instance, rapid infiltration? These are challenging the complexity of response, and we all know that modeling is a kind of a balance between incorporating useful assumptions and sometimes but when one concern is when potentially those assumptions begin to misrepresent conceptually and in practice those responses, and I think that is a challenge. Certainly there is the modelers, and I think we should pay special tribute to those in Frankfurt, Petra Doll and Hans Müller-Schmid and others who have been working on water gap as a global scale hydrological model to incorporate focused recharge processes. And they move towards getting depression generated recharge and other, and I think that's it's a really helpful step in the right direction. One of the other things that the modelers do tend to speak to me about, don't usually come to me for modeling advice, but they definitely do come to me asking me about observations with which they can test their models. And this is, I think, working with people like Scott Giuseco and Deb Peroni at UC Santa Barbara. We've been trying to generate a kind of global scale piezometric data sets, and certainly looking at continental scale and large scale. So one of the things that they need is if they're going to develop new routines in their models, they need to have something to test them against, and ideally calibrate them against, but certainly to test them against. And so it's one thing for us to, you know, myself as a kind of self-confessed empiricist, to further develop the conceptual model. It's important also to follow through by providing observational data sets that the modelers can engage with to refine and improve those models. Perhaps the one thing I will say, and it's not a criticism of the modeling community, and of course we're all in a bit of a, we all have this ambitions to tell the stories that our research is telling, but perhaps we need to maybe step back at times and have a slight greater degree of humility about the uncertainty in our outcomes when we are not representing all the processes, be it focused recharge, macropore flow, and others in our models, and recognize that our models are maybe our best we can do at present, and potentially misrepresentative. But of course, those sort of caveats are not ideally well positioned in the conclusions of high-profile papers, and I appreciate that. We're all you know, we're all part of that. But I think there's a need for us to recognize that our ability to represent the hydrology, and by that I mean also the hydrogeology of the systems. And I think one of the things that I really appreciated in your recent work, Bridget, is the emphasis of thinking about surface water and groundwater as a singular resource. And I think that's vital. And we talked a little bit about that earlier when we were talking about the moisture surpluses in the moist or humid uplands coming down to the semi-arid lowlands and leaking into the groundwater system. So we don't think of surface water as divorced from groundwater, but we realize that they're connected. But in doing so, I think we need to recognize in our modeling infrastructure that hey, we're doing the best we can, but if we're not representing some of these key processes, we need to be a little bit more tentative is maybe the right word. I suppose perhaps the most obvious point to make on that is, if we think of hydrology under climate change, I'm going to give you another paradox, the East African paradox. We started this conversation actually around that, and the fact that the long rains have the failure of the long rains. That's the March, April, May rains in the Horn of Africa, and the observations show that these are declining. And actually, that part of the Horn of Africa and parts of East Africa are moving away from a bimodal system, historically bimodal system of having two rainy seasons, March, April, May, and September, October, November. They're moving now. That suppression of the long rains, March, April, May, is so substantial now that it's really becoming a singular short rain season, meaning that they only really get a substantial regular rainy season from September to November. Now, virtually all of the general circulation models and Earth system models are predicting that the long rain should be going up, but they're going down. And this is called the East African paradox. Well, you can therefore appreciate that none of our predictive models, or almost none of our predictive models, are getting climate change and its impact on precipitation in the Horn of Africa correct. Now that's pretty serious, actually, when you want to think about it. It means anyone using ensembles and ensemble means from the Horn of Africa, the results are, in a contemporary sense, not meaningful, because they're talking about increases when very sharp decreases are observed. And I guess what I'm trying to say is, given that uncertainty and some of our uncertainty about the nature of the recharge processes and how that and what is determining those, I think we sometimes need to exercise a little more humility when we're making our projections or indicating what the impact of climate change is on the water resources of a particular region.
I think you've covered a lot of topics in that response, Richard. And, starting off with the global models and recognizing that water gap is trying to represent the natural processes that we see and that how difficult that is. And also PCR, global water balance, and Mark Bierkens and Yado Pokral, their work to try to understand these things also. And sometimes in the past, before the GRACE satellite data or before the global models, we didn't have a global picture of what was going on, or we didn't have spatial and temporal continuity in what we thought was happening. So these help with that, and we need models for projections and forecasting. So I think, and they test our understanding, so I think that's important. And yes, we have issues with them, but we have to move on all fronts. And I like your comment on trying to provide more data. And I think IGRAC, the International Groundwater Resources Assessment Community, is also trying to provide data and make it readily available for people and researchers and communities to use. So I think that's fabulous, we need data, and we need models, and we need satellite data. And the other aspect, we've been talking about the GRACE satellite data, but for a long time people looked at the vegetation response to rainfalls. And Asaf Anyamba was working with the US Department of Agriculture and showing that during these very wet periods, during El Niños in East Africa and La Niñas in South Africa, that he could see the vegetation response, and then they would predict crop production and stuff like that. So I think we need to look at everything and try to constrain our understanding.
I wanted to like revisit just something there for a minute. I think you raised a really important point, and people like Mark Bierkens at Utrecht and Yoshiwada and the development of the PCR GLOB-WB global model. That's a really good example to follow on the conversation we had, because they brought up through the use of that model the whole business of global scale groundwater depletion and the magnitude of its impact and maybe in its contribution to sea level rise. And even though, and they would admit to that now, the early models, they were a bit crude and they weren't quite correct, but they stimulated such a healthy debate with Lenny Konikow and others so it shows you, even if sometimes the early models aren't correct, okay, they can stimulate, they can lead to a really healthy discussion. And they can also open our eyes to something. I think before Mark and Yoshi had done some of that work, people hadn't really given much thought to the idea that global scale groundwater depletion could be actually making a contribution to sea level rise. And I tip my hat to them both, because that was a huge effort, but it really drove the science along. And now, of course, the models are being improved and revised, and obviously the science is getting better. That's how science works. And I'm now going to make a compliment to you, Bridget. I thought it was great, your earlier paper where you were using the GRACE data to test the outcomes of those global scale models, because really, I think it was such a valuable contribution, because one of the things is it's really hard if you're a global scale model. How do you know if it's right? You put all that effort, all of that work to do it, and you're like, well, could it be right? Might it be right? And I thought that there were some sobering outcomes from your testing of those models with the GRACE data set, but that was really, I think that was a really important contribution to our understanding, and it did show a really important use of GRACE in keeping, I thought a really kind of a wise is maybe the right way to put it, use of GRACE in testing those global scale models.
And I think, it's nice now that they have these model intercomparison projects, MIPS, then they're calculating total water storage and comparing it directly with GRACE, and then using GRACE to constrain their models. So all of these things start to work together. Initially, they may be disaggregated, but more and more, I think we're bringing more and more data. And you talked about how you were bringing water quantity data, piezometric data, and water quality data to understand how the system was working. And so now I'd like to shift a little bit and just maybe talk about the funding sources and the composition of your research teams and the capacity development that you have been able to do in Sub-Saharan Africa through these programs like UpGrow and Grow Futures and all of these. They have been amazing. Maybe you can describe those a little bit, Richard.
Yeah, well, I think one of so UpGrow, unlocking the potential of groundwater for the poor is its what UpGrow stands for, and part of it came out of this understanding of the possible resilience that groundwater resources may provide in the face of climate change that we've been and the issues we've already been talking about before, and so it was wonderful and helpful that the program, largely funded by the government of the UK through its research councils and the so that's UKRI and also the what's now called FCDO, the Foreign and Commonwealth and Development Office of the United Kingdom's government, and that program allowed for the development of consortia. And we have 5 consortia. Grow Futures that I was leading on one was just one of them, and what we were trying to do is capacity strengthening was a key component of this, and the whole nature of this is that the research in country is done by the research institutions and the researchers who are in country, and they are then supported in part of that by funding, but also from if you want to call it guidance and support and capacity strengthening from without. And so really that was those consortia then were establishing and trying to look at it. So there were issues around the reliability of wells and water quality, one called Hidden Crisis, led by Alan McDonald at the BGS. And we were also, our Grow Futures was working in the Sahel, working in Niger and northern Nigeria, but also in Ethiopia and Tanzania. And we're working with the universities in each of those locations. So Addis Ababa University, Soka University of Agriculture, and University of Abu Momoni de Niamey in Niger, and University of Maiduguri. So these research institutions, and then working within in a transdisciplinary way. So this means we're not only working with social scientists considering the equity of these developments and working with communities to understand their aspirations of what kind of development pathways would be desirable or even feasible, but also in the context of not only with the people at the coalface, where we're talking about smallholder farmers or people operating health clinics and that, but also working strategically with national scale government ministries, and be it with ministries of water and agriculture. And the idea was to try to explore and inform policy around how people might be able to use groundwater in a equitable and more sustainable manner in the future. And I think just to give you a little bit of insight from some of that, one of the kind of curious outcomes was that what we found in the communities, in 3 communities, and this is across Ethiopia, Tanzania, and in Niger, we found that people had a strong preference for lower intensity development of groundwater, let's say for smallholder agriculture, and pathways that were perhaps what we might call less impactful on the local ecology. So they weren't trying to maximize benefits. And I think this speaks to a history of understanding that climates are highly variable, and we cannot always be looking to optimize crop yields. We need to be thinking about optimizing, if you will, the resilience of, let's say, crop outcomes or water supply outcomes to potential risks, either from climate or from other sources to those water resources. And I thought that was a really interesting outcome through a really kind of deliberative process that took place, and where communities got together, discussed the pathways, their aspirations, and then scored them using their own criteria, and then coming up with this outcome where the preference or priority put on low intensity, but kind of more environmentally sustainable use of groundwater, recognizing its important contribution to, say, sustaining wetlands or even to dry season river flow. And so that these were some really important insights that came from that. And I'm just going to plug another ad in there, if you don't mind, Bridget. We're now kind of building on that work with under a new program called the Canada-UK Climate Resilience Program, and that's funded by again, the UK government and Canadian governments, including IDRC. And that is working in tropical drylands, and it's deliberately sitting down with communities to try to identify solutions that are ones that the community have identified and want to go. And then we help to look and challenge and test and evaluate the viabilities of those. And these could be slightly top down, like what we might call classic managed aquifer recharge systems with a lot of bit of engineering, or they could be changing crop types or changing different times of the year, or advocating for supplementary wet season irrigation rather than dry season irrigation. So lots of different ways of thinking about that use, and essentially improving the resilience of drinking water supplies and food production to climate variability and change.
I think that's fascinating. And the linkage between water resources and food production, and a lot of the aquifers in Sub-Saharan Africa are small scale aquifers on top of basements. So they wouldn't support the intensive center pivot type of irrigation that we've had in the high plains. And so it's nice to see. But there is almost no irrigation in Africa now, so they could really benefit from some small-scale irrigation that would help them have a more uniform or improve food security in the future. I know when we were working in Brazil on biofuels and stuff, they used the term salvation irrigation, you know, which was sort of supplemental also. And so just, you know, trying to optimize and to balance, you know, water and food security and sustainable development and environmental, considering environmental impacts. So we have a long ways to go, but is your future outlook for Sub-Saharan Africa, are you positive? Do you think it will, you know, with all of these tools that we're starting and all of the data we're starting to bring together, that we will be able to adapt to what we will experience in the future?
Yeah, I'm always an optimist, but not, I hopefully not a naive optimist. I think I was pleasantly surprised by the outcomes from our socioeconomic team around the pathways that people had chosen as aspirational, and that they weren't the let's make the most amount of money and the highest crop return. And that gave me some hope. And I'm not criticizing any other kind of culture, but I'm just saying one of the things I thought was interesting is that when we talk about these, perhaps we might refer to them as low capacity. So they have a generally low transmissivities and low storage capabilities. So these weathered hard rock systems that occupy much of the tropical humid parts of Sub-Saharan Africa. One of the interesting things is those are what we might call essentially self-regulating, because the capacity of the aquifer to deliver water is so limited. It means if someone decides to be a little bit greedy and overpump their system, they are likely only shooting themselves in the foot, meaning their well will bottom out and that will be it, just because they cannot draw storage or flow from very far from their particular property. And that's interesting because perhaps, maybe especially to a North American audience, what may not be fully appreciated is that almost all agriculture or food production in Sub-Saharan Africa is done by smallholder farmers. So hectare-sized plots, maybe a little bit bigger, maybe a little bit smaller. So large-scale intensive farming on very large farms is a rarity. It does occur. There are some flower farms in Ethiopia, and South Africa has some examples, but in Zambia as well. But much of the agriculture is done at very small scale. And so these systems that are essentially self-regulating, they can't overpump. So regional scale groundwater depletion is going to be inhibited just because the aquifer properties are not going to enable that. And I think that's, so I have some kind of hope that some of the problems that we have observed in other parts of the world around groundwater depletion, we may find that that Africa goes its own way, and it chooses different development pathways. So these sort of universal pronouncements that it's a race to the bottom everywhere, I'm not so sure. The other thing I would like to point out is that, there are some conditions, and we can go back to some of the work of Eleanor Ostrom and others and talk about, some of the preconditions for this. You need to know your resource. That's important. Inclusion. You have to have the actors all involved, okay? And really it needs to have a kind of, if you want to call it, the governance architecture needs to be participatory. And I think there are examples, particularly in Peninsular India and other locations in the Indian subcontinent, where that kind of participation and inclusion has been demonstrated and proved to be really effective in moving along what we might call more sustainable pathways, where and that, I think, and certainly the equity is definitely improved by that inclusion and participation. And of course, so I guess I maintain some ambition. Of course, what we know is if you move to the higher latitudes north and south in Africa, so into the Sahara Desert or down into the Kalahari, we are looking at systems that are drylands that are much less frequently replenished. But these large sedimentary systems have a lot of long-term storage. So we might be looking at some strategic depletion issues in those areas, but I guess with an eye to their long-term sustainability. But yeah, so lots of, I think, interesting challenges ahead. But I remain overall optimistic. I don't feel that that the use of groundwater or the potential of groundwater is we might say doomed to follow the same pathways as some other places have fallen. I think it'll be great to improve the dialogue between places like Southwestern United States, California, Central Valley, Rajasthan, Iran, and North China Plain, and to have a kind of almost have a kind of drylands systems and the use of groundwater. We might even form a consortium, Bridget. Anyway, around these issues, so that the sharing of that advice and people might provide some sobering lessons for those that are at an earlier stage in their groundwater development.
Well, thank you so much, Richard. Our guest today was Richard Taylor from University College London, and I'm so grateful for all of the work that you do and the insights that you provide from field studies and then looking at satellite data and models, and the examples that your research programs provide, engaging social scientists, engaging the communities, and the huge amount of capacity development that you have managed through these programs, and all of the professors and the students that are working with you now in Sub-Saharan Africa. It is tremendous. So thank you so much, Richard.
Thank you. I must say that the most rewarding part of the job is watching, if you want to call it, colleagues bloom and go on and now become major players in the international scene around groundwater. And it's so it's lovely. It's wonderful to see that and to think somewhere in the background that one's played a small role in making that happen. So yeah, thanks very much. I really appreciate the opportunity to chat with you, Bridget.